Hey guys, how's everything going? Today, let's continue our journey to LeetCode. Yay! Uh, Today it's 94 binary tree in-order traversal. Do you still remember the in-order, pre-order, post-order? In-order means the root node is in the middle. So if we're given a binary tree of 1 null, 2, 3 null, then 1 is in the middle. So null, 1, 2, 2 is middle. So null 1 3 2 null. So it's 1 3 2. We're going to do the in-order traversal in a textbook. Do you remember that? Still remember that the easiest way is to use recursion? Yeah, this is pretty straightforward. There's already a hint that recursion resolution is trivial. Could we do it iteratively? First, let's start with the easiest solution, is recursion. For me, I'd like to name the recursion function with walk. So I'll create a walk method, which we take a node. If there is left node, then of course we will walk there, right? Because think of a tiny little man. When he stands at 1, he will try to go to the left first. Okay, so if there is no left node, like 1 or 3, we should collect the result. So still const result equals this result push node val. And if there's right node, I walk there, right? So the tiny little man will start at root node. If there is a case, is there a case that it's null? If it's null, if node equals null, return. If that's the case, if we add this null check, we don't need to add the if check, right? It doesn't matter anymore. Return result. Yeah, this easy. It should work. Oh, there's a typo, sorry. It should work. Now let's try to find a way without the recursion. The time complexity of the recursion would be, actually each node will actually be traversed once. So the time would be O linear, and the space we use the one. Of course, the result needs one O linear space, and there's a call stack. The deepest call stack would be linear O big O n. So the worst case is still O big O n. So now let's try to do it in the iteration fashion. How should we do that? I'll remove the code here. By iteration, we're going to rewrite our recursion function. Let's take a look at the tree first. Say if there's a 1, something like this, 1, 2, 3, and then 4, 5. What actually happens is that for the recursion, the little man walks 1, and then because there's left node, so we'll continue walk to the left, and he will continue walk to the left. So he won't stop walking until he finds that there is no left node before the first result is get, right? This collection. Okay, that reminds that every time we walk on some node, we need to walk to the dead end of its left node tree. For example, when he step on 1, actually he needs to start at 4, right? And then we can pop this node and connect to result and walk on the right node. Say if there is a 6 here, it means when I step on 1, I need to go straight forward 4, right? And then collect the result, and then collect the 2, and then step on 5, right? But once I step on 5, I need to step to the dead end of left tree, so it would be step on 6. So 4, 3, 4, 2, 6, 5, and then 1, 3. Yeah, so there's a 2-step, right? The first one is a step, which is walk, and then collect, which is the collect phase. So walk, collect, walk, collect. I'll say I create a new function called walk. We cannot use the recursion anymore. We need to keep track of all the nodes, right? Here we use recursion to walk and walk and walk, but now here we need to keep keep all the tracks of the route we have stepped on, like 1 and then 2 and 4. So we used a stack, which is a array actually, as a track. Use this. Of course, we still need the result. When we walk on some node, we actually won't just add this node to the track, but at the dead end of left node to the track, right? So not only, but we will keep all the tracks, right? So while node is not null, we will keep the track push node, right? Keep just as a step 1, and then keep putting the track. Okay, there's left node, left node 2, 4. Continue to do that. Yeah, this is the walk method. Now we need to start collect, right? How we collect? Well, it's simple, as we have talked about it. When we start collect, there's dead end to the left node, right? We just pop it and start working on the right node, right? So we will pop const top. We'll pop the track pop, and add it to the result. And then if there is right node, and we will work on that also, right? So if node right, but actually there's while check here, so actually we don't need to add if here. We just walk on the top right. And then walk on root and start collect, and then return the result. Wow, isn't it clear? It's pretty clear, right? Actually, we just add a new stack to keep track of this part. It's walk left, walk left, walk left. This is the stack. And yeah, that's all. I think it should work. Oh, it's not working. Let's see. Pop track, push, walk. Oh, God. We need to collect. We need to collect while there is still nodes in the track. My bad. This is on. Yeah. To keep collecting. It should work, I think. Yeah, we accepted, and this is iteration. The time would be the same. Every node would actually be actually pushed and collect. Yeah, actually it's linear and a space. This linear, the track, and most linear, so it's still linear. Well, it doesn't. The time and space complexity doesn't change. But I think it is a common question that will be asked. So please prepare for the in-order or pre-order or post-order. I think if we have time in the future, I will create a separate video for that. Actually, I think there is another way of writing this, which is not that. It's easier to understand, but more difficult to track. I say we separated the walk and collect, but maybe we don't need to do that. I mean, okay, I'll start another way of writing this. So let's take a look at the node again, the tree again. Let's say when we start working on 1, we find that there is 2 nodes here. So the order would be 2, 1, 3, right? So we will, because we're using the array, we could just push these 3 nodes together, right? In this solution, we will push 1, 2, 4 in the stack, but we could just push 3, 3, 1, 2 in the stack, and then we handle 2 because there is 2 nodes. We will push back 5, 2, 4, right? And then for 4, 6, 4, right? Let's try. So what I mean is that let's copy the sample. So first we have 1, and then because we know that there's 2, 3, we will put it as 3, 1, 2. Now we pop again. Okay, I'll put it this. And then we get 2. We find that there's 4, 5. We pushed back again. 3, 1, 5, 2, 4, right? And then 3, 1, 5, 2, 4, 6, 4, right? 6, 4. Yeah. And then let's say this something like this. And then we get 4 again. How should we do it? we get 4 again. Because there's no left node, so we'll pop 4, right? When we pop 4, we pop 4. And then we need to handle 6 if there is left node of 6 or not. But when we do the backward tracking, when we popping the nodes, we don't know if the nodes are handled or not. I mean, we're only sure that the left part of the node is handled. So like for 4, if we push back 6 and 4, we haven't handled 6 yet. So we need to add in the flag to tell us that in the future that 6 needs to be handled. In that case, I will append null here. I mean, when we push the right node into the array, we push the extra null. Like for 1, we push 3, 1, 2. So null here, and null, and 2, 1, 5, 2, right? So 5, null, and 2, 4, 6, 4. So now when we pop 4, we pop until null, and then we handle 6. If 6 is done, we're safe to pop 2 because 4 is already done. So we pop to this null and handle 5 and then 1. So is this clear? Yeah, let's do that. The program will slightly change. I'll say this is a stack. It's not track anymore. The root right here. Okay. While the stack is not empty, we pop the first one. Yeah, const pop equals stack pop. So for now, there are 5 possibilities of this top node, right? If it is a leaf node, I mean, if top left and top right, if it's leaf node, or it has left node, or if it has right node, or it has both. Right? Because the null might be we pushed in. If the root is null, we cannot differentiate which null, what null it is. So I'll add I'll add a special case detection here if root is null. I'll return just empty. So this means that all the null is added by us. Okay, so if it is a leaf node, there's no left or no right. No left or no right. We will do what? We will pop it, right? It's because we just collect the result, and the result push the top. Wow. And we will pop it. It's already popped. So, and we will continue if like this 6, we pop the 6, and we will continue pop to 2. So this is where the null matters. We will pop until null. So while top, we just let top equals stack pop. Result push top val. But this top will affect the top here. It's not that good. I'll say use another one. Okay. Let top equals stack pop. It's not that elegant, but anyway, it makes the things clear. We'll continue pop until null is happen. Null is met. We pop it, and we met null. We push. If we it doesn't matter actually, because yeah, we can use yeah top. We could just use the while loop here. Pop until null is met. Okay, top pop, and now top is met. So null, we could say continue to next round. Okay, and if there is left node but no right node, like let's say there is a 7 here connecting 6. For this case, we will, because there's no right, we just push 2 and 7 back in, right? Okay. So stack push top, stack push top left. Okay, the next one is there's no left but only right. Like 4. Sure, we collect 4 and push 6 in, right? Yeah. Result push top val stack push top right. The last one is if both are there, if 1, 2, 3 is there. If 2, 3 is all there, so as we said before, we push the push top right? And then we add a separator, null, and then push left, stack push top. Oh, there's mistake. This. Okay, here's all the conditions. Let's move back to our example here. Does it make sense? Okay, for 1, we added 3 null 1 2, and then we get 2, so 3 null 5 null 4 2 4, and then we made no left node but only 6, So we add 6 in, so it will actually become 2, 6. And then 6 is popped, there's left node, so 2, 6, 7. Yeah, I think it should work. And then we finally return the result. Let's try run the code. Yeah, it worked. Actually, the time and space complexity doesn't change that much. The results, the worst case, the nodes. It seems to us that this is much verbose. There's an extra judgment of null, make this looks much complicated than this one, right? Walk and collect, it's pretty elegant. But there is one problem that sometimes when we see the problem, we cannot deduct quickly that we should do this, right? We should do the push it to the end something. This is much more, how to say, more easy to come to think personally, because it's naively we want to say we met 1 and then 2, 3, so we better change it to 3, 2, 1, and then handle 2, right? Actually, I think in my personal experiences, I'm not sure whether these are the. I'm pretty sure that these are not the optimal solutions, but adding null in the iteration traversal of trees would be very useful sometime. For this case, we use null to how to say to use null as an identifier. To mark if a node is handled or not, and sometimes like a BFS or DFS traversal for trees, especially for BFS, a null is much easier. Adding null is much easier to do, like for 1 and 2, 3 and 2, 4, 6. Well, it's just a yeah. We will meet. I think I've done some videos about this before. Please search on my channel, like BFS, DFS something. There will be some usage of this null as separator. Okay, so that's all for this problem. I hope it helps. Don't forget to follow my channel, subscribe my channel. See you next time. Bye bye.